We just have a long list, and I think this is gonna be like we'll come to an executive.
Yeah.
I don't think we're gonna do the class by class basis. I think those are want to get ideas from everybody.
But what I was thinking, like if we were going to, is like, you guys can choose like the most popular idea and like the second most popular one to choose for thoughts.
Okay, guys, page 26 in your packet.
I don't think that's.
Like any division can choose.
Okay, so so far we've been looking at graphs of functions, but we haven't been talking about, you know, what does a derivative graph look like? And just to let you know, this will take some time to kind of get used to, but we're going to revisit this over and over again, even into second semester. We're going to, come back to this over and over again because we know we're going to see variations of this on the AP exam. So I want to start introducing it now. All right. Okay. Now let's start off with a function graph. Okay. Let's create a sign line with what we see in front of us. And then I want to talk about how we can translate this onto a derivative graph. I do want to point out a couple of things here. I do want you to highlight 2 points here. -2, 0. And then I want you to highlight the point, the y-intercept here. So purpose of, it may not look quite like it, but let's say that the points of inflections are at x equals 0 and x equals -2. Okay, so points of inflection is where concavity changes, right? Concave down, concave up, concave down. Okay, so let's create an f prime sign line, which is our slope sign line. And tell me where you see relative max and relative min on this graph.
Relative max is that relative min is that y. We don't know it's split.
Yeah, give me the x values of relative max and relative min.
It's the -2. -3.
Sorry, -3. Yeah, you're right, -3. Where else?
0. No, so not 0. -1.
Yeah, I know it doesn't quite line up, but let's just say it's -1. Okay.
And it's +1.
Awesome. Okay. So what about the slopes in each of these intervals here? What's happening to the slope to the left of -3? Positive, followed by negative, followed by, yeah, keeps alternating, right? Okay. Right, so the arrows matches what we see with the graph, right? Even if the graph wasn't in front of us, we should be able to sketch a graph that mirrors the movement of this graph, right? Okay. All right, the y value is not that important for now. Now, let's say we want to create a derivative graph, okay? A derivative graph, a slope graph, okay? So one thing to kind of understand is that first is that your derivative and function graph will not look the same, okay? because the y-axis represents different things between the two graphs. So here, the y-axis for the original function represents the height at each point. Right. So here, this graph, this point has a y value of 0. This point has a y value of, let's say, positive 3, y value of 0, y value of -2, y value of -1. Okay, so on and so forth, right? We're comfortable with the function graph because we've been using it for a long time. Now, what if we had a derivative graph where the y-axis no longer represents the height of the graph at that point, but instead the y-axis represents the slope value at each point? Okay. So it's going to feel a little strange because we're not used to thinking about a graph from a slope perspective. We like to think about a graph from the height or the y value perspective. So anything that has a slope 0 is going to land on the x-axis, right? Because x-axis is slope 0. And then anything with a positive slope, slope 1, slope 2, slope 3, slope 4, slope 5, is going to end up where? Above the x-axis. So I like to indicate what I'm looking at with a little up arrow to indicate anything that has a positive slope needs to live in this upper region. Okay. And then these are all places where my original graph is going to experience a negative slope. So anything below the x-axis is going to represent slope, negative slope. Yep. Okay. So let me ask you, for this graph, where do you see slope zeros on this graph?
Where the curve was.
-3, -1, and 1, right? So we're going to plot the relative max and mins as points on the x-axis. Does that make sense, right? That's a slope 0, slope 0.
So they're like
slope 0. There are x-intercepts now, right? Good. So -3, -1, and 1. All right. Now, I think I'm going to start this way. I'm going to start this way. This is not what you're going to do every time, but I think this will kind of help us see where these numbers are coming from. I don't know what these slopes are at these points, but I'm just going to create some ballpark values. Okay. Now, let's say I start here with a relatively steep slope of 5. Okay. What's going to happen as I move closer towards that relative max? What's going to happen to my slope? Decrease, but it's still going to be what? Still positive, right? Slope 4, slope 3, slope 2, slope 1, right? We're just making an estimation. We just want to show that the slope is becoming more gradual, becoming less steep. Okay. And then as I move towards the right, what's going to happen to my slope?
It's going to decrease, but at the same
Yep.
speed up.
Good. -1, -2, -3. But then eventually it's going to start moving towards
Positive again.
yeah, 0, right? So let's say -3 again, -2, -1, 0. Okay. And then let's keep going. 1, 2, but then it's going to start moving back towards 0, right? 1, 0. And then what's going to happen as I move to the right?
It's going to decrease.
-1, -2, -3, -4. Okay, so now imagine you're plotting these values on this graph. So anything to the left of -3, where is my graph going to live? Above or below the x-axis? Above, right? So 5, 4, 3, 2, 1. It's decreasing, right? My slope is decreasing, but it's still above the x-axis. So this could be a y value 5, slope of 4, slope 3, slope 2, slope 1, slope 0. Okay. All right. From here, what's going to happen? It's going to start dipping below the x-axis, right? -1, -2, -3, but then eventually it's going to loop back up to 0 at -1, right? So it's going to do something like this. We don't have to worry about how accurate it is, but we do know the graph is going to do something like this, right? Does that make sense? -1, -2, -3, -3, -2, -1, 0. All right, and then from here, it's going to start going back in the positive direction, but then it's going to have to come back down, right? 1, 2, 1, 0. And then from here, what's going to happen? -1, -2, -3, -4 below the x-axis. Okay, so we're plotting slope values as y values on the graph. So it feels a little strange, right? And as you can suspect, it's not going to look the same, right? Because this y value is not going to match up with the slope value at that point. So obviously it's going to look very different.
You had arrows though.
We can or not. It's yeah, sure.
Would we want like this for like concavity too?
Yeah, we're gonna do one for a second derivative graph as well. Okay, so but are we okay here? Okay, we're going to the more common thing is where we have to start with the derivative graph and work backwards, but we'll get to that. But I think this is more straightforward, looking at the function graph and then working our way to f prime. But okay, we'll come back and revisit this. Now, let's see if we can create a graph or sine line for concavity. So let's draw a line here, and we'll do a second derivative sine line. So now I want us to consider where are the points of inflections are going to go onto my f double prime sine line, right? And I've already established that points of inflection are at -2 and 0. Okay, so go ahead and put those onto your f double prime sine line. Okay, so what you see is what you get. What do you expect from concavity for my original?
Concave down.
Concave down.
And concave up.
Yep.
And concave down.
Good. Okay, so concave down, concave up, concave down. Okay, we're going to take this and put it onto an f double prime graph. And again, the y-axis is going to change its definition. The y-axis is no longer going to represent the height of the graph. It won't represent the slope value of the graph. It's now going to represent the what of the graph? The concavity. So anything that is concavity value of 0, which are potential points of inflections, will go on the x-axis. Anything that is what will be above the x-axis?
Concave up.
Concave up. So I'm going to indicate that's where the graph's going to live. And then anything that's concave down is going to live below the x-axis. So guess what is going to be placed onto my f double prime x-axis? Yep. So -2 and 0. Now these are going to act as anchor points. We know that whatever we draw, our graph is what's going to link through those points. Okay. Now, where do we want the graph to live to the left of -2?
Towards the bottom.
Okay, so to the left, below the x-axis. But it's got to link up to this point because we've established this point. So it's going to rise to that point. Does that make sense? Do not worry about the shape of the graph. The shape of the graph is not going to match this. Okay, the shape will match the original graph because that's concave down, concave up. But your shape is not going to match second derivative because this is defining completely something different. It's not the y value, so the graph will look different. Okay, where do you want the graph to live between -2 and 0? Above, but it's going to have to come back down, so it's going to be a loop. We don't have to worry about how high or how low it goes. You just have to make a loop down. And then what's happening to the right of 0?
Going back down.
Going back down. Okay.
Kind of ironic how, like, for like demonstrating a concave up graph, you're like drawing a concave down.
Well, yes, this is concave down shape, but it's obviously not. The only reason why we call it concave down is because that's the shape of the original graph. But we don't want to ever associate the shape with the second derivative graph, right? It's something different. Because the y-axis now represents something different, so the graph is not going to mean the same thing. Okay, I do want to point something out here. This original graph, let's say this is a degree 4. So let's say this is y equals negative x to the 4th. Right. I mean, there may be other coefficients, or other degrees, but we know this is a degree 4, right? It has 3 direction changes. So what's the derivative of negative x to the 4th? Negative 4x cubed. This is a cubic function, right? You see the derivative graph? It matches the cubic function. So it's nice to see that link. Okay, what's the derivative of negative 4x to the 3rd? Negative. This is a quadratic function. And then we see that mirrored here with the graph as well. So it's nice to see that connection between, oh, the graph that we create matches the derivative that we know is for power rule. Okay. Now, before we go to the next page, I do want to point something out here. Let's say I started with the f prime graph, and I'm asking you to create the f prime sign line. And then from there, we're going to create the graph. So what we're going to do is whenever you see the f prime graph and you're starting with this, you're going to start labeling your graph. So slope 0, positive slope, negative slope. Your critical points will be your x-intercepts. So you're going to place them onto your x-intercepts, onto your slope sign line, -3, -1, and 1. Anything that is above the x-axis, I know the graph is falling, but look at the location. That is above the x-axis. So you know that is going to mean the original graph is going to be rising. The only reason why this looks like it's falling is because the slopes are becoming less steep. So that's why it looks like it's falling. But it is still above the x-axis, so it's still a positive slope. And then anything that is below the x-axis, you can translate that as a negative slope. Anything that is above the x-axis, positive slope, and then below is negative slope. And then once we have this sign line in front of us, we can just sketch the graph based off of the arrows that we see. Rising, falling, rising, falling, relative max, relative min, relative max. Okay. Okay, and then the other thing that will take some time to get used to is that we can also gather points of inflection of the original graph from the f prime. Now, look at your points of inflection and look at your f prime graph. Where do you see them show up on the f prime graph?
X-intercept.
Well, not x-intercept. Where's -2 and 0 on the f prime graph?
Oh, f prime. Sorry.
Relative max and relative min. Okay. Now, these are places where your maximum and your minimum steepness is occurring, right? And so that is mirrored here on the graph. The steepest place on my graph is my points of inflection. And so the highest and lowest steepness will be represented as peaks and valleys. So the peaks and valleys of your f prime graph will represent the points of inflections of your original graph. And then wherever my slope is moving in a negative direction, that's going to correspond to where the original graph is going to show concave down. Positive slope, wherever my graph is becoming, where the slope is becoming more positive, is going to translate to concave down, sorry, concave up. And wherever my slope is becoming more negative, it's going to translate to concave down. Okay, it's a lot that I'm throwing at you right now, but I just want to start introducing that, and then we can kind of cycle back to that over and over again. Yeah.
Why did you like we're gonna have like the y equals like negative x to 4, y prime equals negative 4 x to 3, and y double prime equals negative x squared?
I just want to show that the shape matches what we see with the derivative, right? A negative x to the 4th looks like this. A x cubed looks like this. And x squared looks like this. So what we see from a derivative standpoint, power rule wise, can also be demonstrated with the shape of the graph.
Parent functions.
Yeah, parent functions, right? But you see how the curve is becoming less, just like how we would expect from a derivative, right? Okay, all right, so let's go to the next page here, page 27, number 3. Now we're gonna look at an F prime graph. Okay, so what we're gonna do is this is what your test will feel like, okay, in the sense that this is what I'm gonna give you. I'll give you an F prime graph. I'll ask you to sketch the f of x, f double prime, and I'm gonna ask you information about the original graph based off of the F prime. Okay, so we're gonna practice 2 of these, kind of getting a feel for how AP exam likes to ask you questions, as well as how I'm going to ask you on the test.
Oh, so they give you the F prime graph.
I'll give you the F prime graph, and I'm going to ask you what is the original, or I'm going to ask you information about the original graph, but you're going to pull that from an F prime graph.
Do you recommend like scheduling like the normal graph first?
So here's what I suggest. I'm going to suggest that we create our slope sign line, because your slope sign line will give you a very rough picture as to what the graph looks like. And then we're also going to create a second derivative sign line. And then once we have the sign lines in front of us, we're going to sketch the graph based off of the sign lines, but we're not going to look at the graph anymore because the graph is going to be confusing. What students do is if you start looking at the F prime graph, you're going to start sketching a graph that looks just like F prime. And we know these are not going to look the same. Right. So I want us to start off first understanding this is not the original graph. This is the slope graph. So the y-axis does not represent height. It represents the slope value of the original graph. So let's just start off by labeling what we see in front of us so that it makes it easier for us to interpret what we're working with. So I want you to start off this way, okay? Do slope equals 0 on the x-axis, positive slope above the x-axis, and negative slope below the x-axis. Okay, let's create a slope sign line. And tell me, where is the original graph going to experience slope 0? Wait, where's the original graph going to experience slope 0? Slope 0 is going to be where the x-intercepts are, right? Okay, so the x-intercepts, so -3, where else? -1 and 1.
What was the question?
Where is the original graph going to experience a slope 0?
Oh, and that's where like that changes from.
Where it changes signs, x-intercepts, right? Because what is the y value at this point? 0. And remember, the y value now represents the slope value. So the slope value, when slope 0, are going to land on the x-axis, right?
I think it's over, right?
Oh, sorry, -4. My bad. Sorry, guys. That's why you're confused. Okay, so -4. Where else?
-2.
And 1. Sorry. Okay, so obviously this is not the original graph. If this was the original graph, we would say slope 0 is at, these peaks and valleys. So what's happening to the left of -4? I know it's rising, but where is it located? Under. So that's going to represent negative slope. I know it looks like it's rising, but these are all negative values becoming less negative. That's what that rising is doing. Okay. What's happening between -4 and -2? Because it's above the x-axis, right? The loop just indicates that these are all different variations of positive slopes, but these are all still positive slopes because these are all above the x-axis. Okay. What's happening between -2 and 1? Below the x-axis. Okay. What's happening to the right of 1? Decreasing. Okay. Now, I also want us to create an F double prime sign line. F double prime is where we're going to pick out the points of inflections of the original graph. Where can we find the points of inflections of the original graph based off the F prime graph? Yep, peaks and valleys. Because these are going to be where the maximum and minimum steepness of the original graph is going to occur. and that's going to be the points of inflection. Okay, so where are the points of inflections?
-3, -1, and 1.
So on the second derivative sine line, we're going to gather information about concavity. So now we look at the slope. Wherever the graph, the f prime graph is rising, that means the slope is becoming more positive. If the slope is becoming more positive, that means it's going to represent what? Concave up. Concave up. Okay. Here, slope is becoming more negative, so therefore concave down. Slope is becoming more positive,
Concave up. Concave down.
and then concave down. Now, we're going to sketch the original graph, but I think this is helpful. Okay, I want you to cover up the original graph, or cover up the f prime graph, because if you are looking at the f prime graph and trying to sketch the original graph, what's going to happen is you're just going to naturally want to create the graph that you see in front of you. Okay, it just makes it more confusing. Pretend like you don't have anything to work off of except for this sine line. Okay, that's the only thing you work off of, which means that we may all pick different mins and maxes, but it's okay as long as the shape of the graph is matching this slope behavior, you'll get full credit. Okay. All right. So what do you expect at -4? Relative
Downward
what?
slope.
Okay. Yeah. And then what do you expect at -4 though? A relative what?
Minimum.
Minimum. Now you can make your relative minimum anywhere you want. I'm just going to make it lower on the graph. Okay. So I'm just going to pick an arbitrary point. You can pick a point higher or lower than me, but you know your graph is going to be some relative min. Okay, what do you expect at -2? Okay, I'm going to just pick a high point just to make it where I can distinguish my graph a little bit more. And what about at 1? Yeah, it's falling, but is it a relative max, relative min? It's not. So I know it's just going to kind of flatten out, but I'm just going to pick a relative, a point somewhere in between. Now, I want you to sketch the graph. We don't care about the curvature right now. We just want to sketch the graph based off the slope, right? So negative slope, positive slope, negative slope, negative slope. Okay. All the while, we're not looking at the f prime graph, right? Don't look at this anymore. It's going to be confusing.
So you like horizontal right there?
Yeah, I'm making it I'm making a slope 0 here because we know at 1 there's a slope 0, right? Okay. But it's neither a max nor a min. Okay, we're going to add the curvature information into this graph. So at -3, wherever the graph lands at -3, just go ahead and highlight that point. I'm going to pick a point somewhere here, okay, because that's where my graph landed. Pick a point at -1, wherever your graph lands at -1, go ahead and highlight that point. And wherever your graph lands at 1, go ahead and highlight that point.
Already there, right?
Yeah, it's already there, yeah. So now we already have the path of the graph. We're going to retrace it with the curvature that we expect. First is what? Concave up. Let's make it, let's over exaggerate it a little bit here. Concave up, followed by
Concave down.
Concave down to my next red dot. Next up,
Concave up.
concave up. And then next,
Concave down.
concave down. Okay. I really think it's important when you create your slope and concavity sine line, visually cover up your f prime graph, because I saw with my BC students when they took this test, they started copying the f prime graph, and it looked the exact same, even though they had their sine lines in front of them. So, okay, still covering up your graph. I want us to create an f double prime graph based off of just this sine line. It's the only thing that we're working off of. Okay, go ahead and label what you know to be true about your second derivative sine line, because, second derivative graph, because your y-axis now represents something completely different. It represents the concavity value and not the slope and not the height. So guess what we can place onto our x-axis?
Points of inflection.
Good. -3, -1, and 1. Okay, where do we want the graph to live to the left of -3? Above. Okay. Now, you're just going to make a straight line down. Okay. I know you're going to be tempted to want to make the graph look like this shape, but understand that this shape is just to show that it needs to live above the x-axis. Okay. You're not going to make the graph look like these shapes because these shapes are coming from the original graph. Okay. Those the shapes is it's just for us to name concave up, concave down, but we're at the second derivative level, so the shape is not going to be as there's not going to be as many curves as the original graphs. Okay, so just make a graph that is basically looks like a linear graph. Okay? You're just going to make the graph fall. Do not try to create all these curves because it's not going to happen. Right? Where do we want the graph between -3 and -1?
Negative below the x-axis.
Below. But this one we're going to make slightly curved because it has to loop back up to this point, right? So in this case, we are going to curve it, but we're not going to.
Curve.
Yeah, just a small curve, right? It's not, we're not going to, don't match the shape, right? Just match the location. That's all we need to
We don't
do.
care about distance, right?
No, yeah, it doesn't have that. It's going to be a little bit, it can be a little bit, it can be higher. Yeah, it's the shape I'm after. Okay, what's happening between -1 and 1?
Positives above it.
Above, but it has to come back down, right? Because that point is telling us where we need to go. Okay, and then to the right of 1.
Negative, so it goes down.
Okay, so now the easy part. We're going to fill in the characteristics, but you're just reading everything off of your sign lines, right? Your sign lines, don't look at your graphs anymore. Your sign lines will tell you everything. Okay, so where's my graph increasing?
From -4 to -2.
Yep. Where's my graph decreasing?
-2 to positive.
Okay, you can say that, but I'm going to encourage us to always separate our intervals. In this case, you can combine it, but if we always separate it, then we never have to run into any issues. But first, let's start with the left side, though. How about this region? Okay. Okay, and then, yeah. Yeah, 1 to positive. Okay, where's my relative max? Yeah, I don't know what the y value is, but I just have to, I can tell what my x value is. Relative min. Yeah, we don't know what the y value is. You can create your own y value if you wanted to, but we can just.
There's only one increasing characteristic.
That's right, there's only one increasing. So from -4 to -2. Okay, all right, where's the graph concave up? Okay, where's the graph concave down? Points of inflections. We don't know what the y value is, right? So x is at. Good. Okay. Questions?
Would there ever be a case where they give you like the F double prime graph you have to solve?
If I gave you the F double prime graph, then all I can ask you for is the points of inflections and the concavity. I won't ask you to create the F double prime graph off the F double prime graph.
Yeah, you probably have to give us more information.
Exactly, right. So what's going to happen on the test is I'll give you the F prime graph and I'm going to ask you to do these things. But you can, but yeah, if I gave you F double prime graph, the only thing I can ask you for is points of inflection and concave up, concave down. That's all I can ask you.
You always recommend doing the original function graph first, right?
Yeah, that's fine. Okay, why don't we start number 4, see how much we can do, and then I'll follow up with the steps. But use number 3 as your model. And then once you create your sign lines, visually cover up your f prime graph because it's just going to confuse you when you're trying to sketch your graph. Sorry, let me call this f prime again. F prime, f. I mixed the letter between f and g here. Page 27. Okay, are we good with the x-intercepts representing the potential relative max, relative mins? Okay. All right, what do we put to the left of -2? Increasing. I know it's going to be tempting to say decreasing because that's what the graph looks like, right? But that decreasing is telling us something else, right? But these are all positive slopes. These are just becoming less steep, but it is still above the x-axis. So look at the location. Don't look at the movement. Look at the location. Between -2 and 1? Still positive. Yep, still above the x-axis, right? Between 1 and 3, below the x-axis. To the right of 3.
Or no, it's negative.
To the right of 3, above
Oh,
the x-axis, right? Yeah, above the x-axis. Okay. Okay, good. Let's create our f double prime sign line. We're going to gather information about points of inflection and then concavity. So where are the points of inflections going to live if we're looking at the f prime graph?
-2,
Good.
0, and positive.
Good. Peaks and valleys. Okay. Now we can look at the movement of the graph. Okay. What do you think this is going to represent? Negative slope means
Negative. Let me concave down.
concave down because this represents, these are all positive slopes, but the slope is moving towards a negative value or becoming more negative, and that is going to end up shaping like a concave down graph. I know you're going to be tempted to say, oh, this is concave up, concave down, concave up, but this is not the original graph, right? So this is still the shape is not going to match what we expect from a graph. Okay, so look at the slope, concave down for a negative slope. Well, remember this y-axis doesn't represent the concavity value. This represents the slope value. So imagine a slope of 5, 4, 3, 2, 1. The slope of 5, 4, 3, 2, 1 is going to look like this, 5, 4, 3, 2, 1. So a negative slope on the f prime graph is going to end up shaping like a concave down. Yeah, I know it's going to take some time, but I'm glad you're asking those questions. Okay, between -2 and 0,
Concave up.
because the graph is becoming, the slope is becoming more positive. Right. Okay, between 0 and 2,
Negative.
negative slope means concave down, and then positive slope means concave up. Okay, I want you to do what you can to cover up your f prime graph, because that's just going to confuse you if you're trying to sketch the original graph. Okay, so imagine you're blind to the f prime graph. All you're able to work off of is these arrows that you see in front of you. So, do I see a relative max or relative min? At 1, I have a relative max. I'm going to just arbitrarily choose a point that is relatively high, but you don't have to. How about, well, what happens at 3?
Oh, yeah.
Okay. At 3, relative min. So I'm just going to exaggerate a low point. Okay. What about -2?
No.
But it's just maybe some value in between, right? Because I want my graph to rise, rise, fall, and rise. So just based off these arrows, Now, your points may be different than mine, which is fine. We just want to make sure that the movement of our arrows are the same. So we want to rise to -2, flatten out, rise to a relative max at 1, fall to a relative min at 3, and rise after that. Okay. Cover up your F prime graph. Don't look at your graph anymore.
Why is it like horizontal and -2?
Because what's happening at -2? There's a slope what? Slope 0. So it's going to flatten out for a moment. Right, slope 0, slope 0, slope 0. Okay, now off of your sketch, where can our points of inflection will be at -2, 0, and 2. So wherever your graph lands at -2 and 0 and 2, go ahead and highlight those points. And now we're just going to retrace the graph with the proper curvature. We start with concave down, then concave up, then concave down, then concave up. Okay, your homework is page 28 and 29. I will send out a reminder, and I'll send out a link to the key as well. Okay, we'll do optimization on Monday, but I'll send out a reminder over the weekend. Okay, come get your phones.
Do you feel like I said, it's like it's just the it's like all we learned. I looked at my computer. No, I probably last week we that all in. You guys think you lose 5, 6 period. But you're my advisor in 3rd period.
Yeah.
Can you tell me how to I'm kind of scared. How you doing on those reading